The universe does not end at the edge of our solar system. Beyond the orbit of the outermost planets, beyond the slow drift of comets at the very limits of the sun's gravitational reach, space continues. And not far beyond that boundary, in astronomical terms at least, there are other stars, other suns, and orbiting some of those suns, other worlds. Tonight we are going to spend some time with the nearest of those worlds, the planets that astronomers have detected just outside our solar system, in the star system closest to our own. We will look at how those planets were found, what we know about their surfaces, their atmospheres, and their relationship to their star. We will consider what makes a world genuinely capable of supporting life, and why that question is more complicated than it first appears. And we will reflect on what it means that the nearest planets beyond our sun are already teaching us things we did not expect to find. There is no rush tonight. These are ideas worth sitting with slowly. This is Sleepy Time Universe, where the biggest questions in science are explored at the pace of a calm and restful night. Chapter 1. The Nearest Star System. The star system closest to our Sun has a name that most people have heard at least once: Alpha Centauri. It appears in science fiction, in conversations about interstellar travel, and occasionally in news articles about exoplanet discoveries. But the name tends to travel further than the understanding of what it actually is. So tonight we begin there, with a clear and unhurried look at what Alpha Centauri really consists of, how it was discovered, and why it occupies such a particular place in the history of astronomy. To start with the basics, Alpha Centauri is not a single star. It is a system of 3 stars, all gravitationally connected, all moving together through the galaxy as a group. 2 of those stars, designated Alpha Centauri A and Alpha Centauri B, form what is called a binary pair. They orbit each other over a period of just under 80 years, locked in a slow gravitational dance around a shared center point. In size and character, both are broadly similar to our own Sun. Alpha Centauri A is slightly larger and brighter than the Sun. Alpha Centauri B is slightly smaller and cooler. Neither is dramatically different from the star we orbit. They are, in the language of stellar classification, Sun-like stars, which is part of what has made this system so interesting to astronomers studying the conditions around nearby stars. From Earth, the 2 stars of the binary pair appear very close together in the sky. Seen from southern latitudes, they form what looks to the naked eye like a single brilliant point of light, the 3rd brightest object in the night sky, after Sirius and Canopus. Only a telescope reveals them as 2 separate suns. They sit approximately 4.37 light-years from Earth. That distance is worth pausing on for a moment. A light-year is the distance light travels in a single year, moving at roughly 300,000 kilometers per second. In 1 year, light covers nearly 10 trillion kilometers. Alpha Centauri A and B are 4.37 times that distance away. In terms of space travel, even at the speeds of the fastest spacecraft humanity has ever launched, a journey there would take tens of thousands of years. And yet, on the scale of the galaxy, which stretches roughly 100,000 light-years from edge to edge, Alpha Centauri is essentially next door. The binary system was first recorded as a double star in 1689 by a Jesuit priest and astronomer named Jean Richaud, who noticed the 2 components while observing a comet from Pondicherry in India. Over the following centuries, it became one of the more carefully studied star systems in the southern sky, partly because of its brightness and partly because of its proximity. By the 19th century, Astronomers had used careful measurements of its position over time to calculate its distance with reasonable accuracy, making it one of the first star systems beyond our Sun, for which a reliable distance was established. But the story of Alpha Centauri grew considerably more interesting in the early 20th century, when a third member of the system was identified. In 1915, a Scottish astronomer named Robert Innes was working at the Union Observatory in Johannesburg, South Africa. Using a technique called blink comparison, which involves switching rapidly between two photographic plates taken of the same region of sky at different times, he noticed that a faint star had shifted its position noticeably between the two images. The amount of that shift was similar to the proper motion of Alpha Centauri A and B, meaning the faint star appeared to be moving through space in roughly the same direction and at roughly the same rate. Innes concluded that this dim point of light was not simply a background star. It was a companion, gravitationally associated with the binary pair. Further measurements confirmed his conclusion, and they revealed something additionally surprising. This third star, which would come to be known as Proxima Centauri, was actually slightly closer to the Sun than the bright binary pair it accompanied. Its name reflects that finding. Proxima comes from the Latin for nearest. At a distance of approximately 4.24 light years, Proxima Centauri holds the distinction of being the closest known star to our solar system, a title it has held ever since its identification over a century ago. The three stars of the Alpha Centauri system are bound together by gravity, but they are not arranged in a compact cluster. Alpha Centauri A and B orbit each other at a distance that varies between roughly 11 and 36 astronomical units, where 1 astronomical unit is the average distance between Earth and the Sun. Proxima Centauri, by contrast, sits at an enormous distance from the binary pair, approximately 13,000 astronomical units away, or about 0.21 light years. It traces a very slow orbit around the central binary, completing one circuit over a timescale estimated at roughly 500,000 years. How Proxima ended up in this arrangement is still an open question in astronomy. One possibility is that all three stars formed together from the same cloud of gas and dust, which would mean they share a common chemical history. Another possibility is that Proxima formed elsewhere and was gravitationally captured by the binary system during a close encounter in the early history of the galaxy, eventually settling into its current distant orbit through a combination of gravitational interactions. Both scenarios have been explored mathematically, and current evidence suggests the first is more likely, though the question has not been fully resolved. What is clear is that Alpha Centauri, taken as a whole, represents something genuinely unusual in our astronomical neighborhood. It is the nearest stellar system to our own. It contains multiple stars of different types, and as we will explore in the chapters ahead, it has turned out to contain planets as well. The nearest stars to the Sun are not empty, they are occupied, and understanding what occupies them has become one of the more active and consequential areas of modern astronomy. Chapter 2. Proxima Centauri. Of the three stars in the Alpha Centauri system, Proxima Centauri is the one that has attracted the most sustained scientific attention in recent years. This is partly because of its record-holding proximity to Earth, and partly because of what has been found orbiting it. But before we get to those discoveries, it is worth spending some time with the star itself, because Proxima Centauri is a genuinely unusual object, full of characteristics that seem to contradict each other at first glance. Proxima Centauri is classified as a red dwarf star, which places it in the most common category of star in the Milky Way. Roughly 3/4 of all stars in our galaxy are red dwarfs. They are small, cool, and dim compared to stars like our Sun. Proxima itself has a mass of approximately 12% that of the Sun, and a diameter of around 15% of the Sun's. If you were to place Proxima Centauri and our Sun side by side, the difference in scale would be immediately striking. The Sun would dwarf it completely. And yet, despite its small size, Proxima is denser than our Sun by a considerable margin, packed more tightly, with stronger gravitational compression relative to its volume. The surface temperature of Proxima Centauri is significantly lower than that of the Sun. Where the Sun burns at roughly 5,500 degrees Celsius at its surface, Proxima sits closer to 3,000 degrees. This cooler temperature is what gives red dwarf stars their characteristic reddish hue, though in practice, Proxima is too faint to be seen with the naked eye at all. Despite being the nearest star to our solar system, it requires a telescope to find. This was part of why it went undetected for so long after the bright binary pair of Alpha Centauri A and B had already been catalogued and studied. The low luminosity of Proxima Centauri is one of its defining characteristics. It produces only a small fraction of the energy output of our Sun, which has significant consequences for any planets orbiting it. A planet would need to sit very close to Proxima to receive enough warmth for liquid water to exist on its surface. This is a theme that will come up repeatedly as we explore the planets of this system, because proximity to the star creates its own set of complications, as we will see. One of the more remarkable facts about Proxima Centauri concerns its lifespan. Stars consume hydrogen as fuel through nuclear fusion in their cores, and the rate at which they burn through that fuel determines how long they live. Our Sun is estimated to have a total lifespan of around 10 billion years, of which it has used approximately half. Red dwarfs burn their fuel far more slowly. Proxima Centauri is predicted to remain on the main sequence, the stable hydrogen-burning phase of a star's life, for approximately 4 trillion years. That is 4,000 billion years. The current age of the universe is around 13.8 billion years. Proxima will still be burning long after our Sun has exhausted its fuel and collapsed, long after our entire solar system has transformed beyond recognition. In cosmic terms, Proxima Centauri is a star built for the very long run. This extraordinary longevity comes from a combination of factors. The low mass means the core fusion reactions proceed slowly and steadily. And unlike the Sun, which has a layered internal structure with a radiative zone separating the core from the outer convective layer, Proxima Centauri is believed to be fully convective throughout. Material circulates continuously from the core to the outer layers and back again, meaning that fresh hydrogen is constantly being mixed into the core rather than sitting in separated layers. This gives the star access to a much larger proportion of its total hydrogen supply over time. In essence, Proxima makes efficient use of everything it has, which is why it can sustain itself for so much longer than a larger, hotter star. That same fully convective interior also has consequences that are less benign, at least from the perspective of anything orbiting the star. The churning of material throughout the star generates strong and complex magnetic fields, and those magnetic fields are the source of one of Proxima Centauri's most defining and most studied characteristics, its intense and unpredictable flare activity. That is where we turn next. Chapter 3. A Star of Contradictions. When Robert Innes identified Proxima Centauri in 1915, it was immediately recognized as a paradox. Here was the nearest star to the Sun, and yet it was among the faintest stars then known. The closest stellar neighbor was not a beacon. It was barely a whisper of light. But as the 20th century progressed and instruments improved, astronomers discovered that this quiet appearance was misleading in important ways. Proxima Centauri, it turned out, was anything but passive. In 1951, the American astronomer Harlow Shapley announced that Proxima Centauri was a flare star. This classification describes stars that undergo sudden, dramatic increases in brightness and energy output, caused by explosive releases of magnetic energy from their surfaces. At the time of Shapley's announcement, Proxima was identified as the most active flare star known. The star that was simultaneously the nearest and the faintest was also the most energetically volatile. The paradoxes were accumulating. To understand what a flare actually is, it helps to think about what is happening inside and at the surface of the star. The fully convective interior of Proxima generates magnetic field lines that rise through the star and emerge at its surface. When these field lines become twisted and tangled, they store energy. Eventually, that stored energy is released in a sudden burst, an explosion of radiation that flashes across the electromagnetic spectrum. These flares emit light at wavelengths ranging from radio waves through to visible light, ultraviolet radiation, and X-rays. They can be extraordinarily intense, and they can occur without warning. Observations of Proxima Centauri have shown that its surface is magnetically active across a very large proportion of its total area at any given time, far more so than our Sun, even during the peak of its 11-year solar cycle. The baseline level of X-ray emission from Proxima, measured during its quieter periods, is comparable to that of our Sun, which is a striking fact when you consider how much smaller and cooler Proxima is. During a flare, that baseline can increase by factors of hundreds or even thousands within a very short period. In May of 2019, astronomers recorded the most powerful flare ever observed from Proxima Centauri. The event was detected across multiple observatories and instruments, capturing the flare in different wavelengths simultaneously. The burst of ultraviolet radiation alone was intense enough to raise serious questions about conditions on any nearby planet during such an event. This was not a subtle fluctuation. It was a dramatic and rapid transformation in the star's energy output, lasting only a short time before subsiding, but carrying enough energy in that brief window to have significant effects on anything exposed to it at close range. What makes this particularly relevant to the question of planets is the distance at which a world would need to orbit Proxima to receive adequate warmth. Because the star is so faint, that distance is very small. A planet in Proxima's habitable zone, the region where temperatures might allow liquid water on a surface, orbits at roughly 5% of the distance between Earth and our Sun. At that distance, the planet is exposed to the full intensity of every flare the star produces. The radiation environment is not gentle. It is, by the standards of our own experience in the solar system, extreme. This creates one of the central tensions in the study of red dwarf planets. Red dwarfs are the most common stars in the galaxy. Many of them host planets. Some of those planets orbit within the habitable zone. At first consideration, this sounds like good news for the prevalence of potentially life-supporting worlds. But the same characteristics that make red dwarfs long-lived and common also make them hazardous neighbors for any planet close enough to be warm. The radiation environment, the particle flux from flares, and the powerful magnetic effects can erode planetary atmospheres over time, strip away surface water, and bombard any potential biology with damaging high-energy radiation. None of this makes life impossible around red dwarfs. Life is resilient, and we know very little about the full range of conditions under which biology can emerge and persist. But it does mean that the question of habitability around stars like Proxima Centauri is considerably more complex than a simple calculation of distance from the star. We will return to that complexity in detail when we examine the planets themselves. For now, it is enough to hold the picture of Proxima as it truly is: a small, ancient, extraordinarily long-lived star, dim and quiet in appearance, but capable of releasing enormous bursts of energy without warning. A star of genuine contradictions. Chapter 4. How we find planets. We cannot see. One of the most remarkable things about the exoplanet discoveries of the last 3 decades is that almost none of the planets involved have ever been directly photographed in any meaningful sense. We cannot point a telescope at Proxima Centauri and see its planets the way you might look through a window and see objects on a table. The planets are far too small, far too dark, and far too close to the overwhelming brightness of their star for direct imaging to work in most cases. And yet we know those planets are there. We can measure properties of their orbits and estimate their masses. The methods by which astronomers accomplish this are worth understanding, because they shape everything we know and everything we do not know about the worlds beyond our solar system. The first method to consider is called radial velocity measurement, sometimes referred to as Doppler spectroscopy. It is based on a simple physical principle. When a planet orbits a star, it does not simply circle a stationary object. Both the planet and the star orbit around their shared center of mass. For very large planets, this means the star itself moves in a small but measurable orbit, wobbling slightly as the planet pulls on it gravitationally. This wobble causes the star to move very slightly toward us and then away from us as it completes each cycle. When the star moves toward us, the light it emits is compressed slightly toward the blue end of the spectrum. When it moves away, the light is stretched toward the red end. By measuring these shifts in the star's spectrum with sufficient precision, astronomers can detect the wobble and from it infer the presence of a planet, along with information about the planet's orbital period and minimum mass. This method was used to detect the first confirmed exoplanet orbiting a Sun-like star in 1995. It has since been used to find hundreds of planets, including some of the worlds orbiting Proxima Centauri. The technique is particularly sensitive to large planets orbiting close to their stars, because those configurations produce the strongest and most frequent wobbles. Detecting a small planet through radial velocity requires extremely precise instruments, because the wobble it induces is correspondingly tiny. The detection of Proxima Centauri d, one of the system's smaller worlds, pushed the limits of what radial velocity measurement could achieve at the time of its announcement. The second major detection method is called transit photometry. This approach involves monitoring the brightness of a star very carefully over time. When a planet passes in front of the star from our perspective, it blocks a small fraction of the star's light, causing a brief and repeatable dimming. By measuring the depth of that dimming and the interval between successive transits, astronomers can determine the planet's size relative to the star and its orbital period. The Kepler Space Telescope, launched in 2009, used this method to survey a large patch of sky and discover thousands of planets around distant stars. Its successor, the TESS mission, expanded that survey to cover a far larger portion of the sky. A third method, gravitational microlensing, works on a very different principle. When a massive object passes between Earth and a distant star, its gravity bends the light from the background star in a way that momentarily amplifies it. If the foreground object is a star with a planet, the planet's gravity adds a brief secondary signal to that amplification. This method is sensitive to planets at a wide range of distances from their stars, including those that other methods might miss, and it has been used to discover planets that would otherwise be undetectable. Its limitation is that the alignment required is rare and unpredictable, and observations cannot be repeated for the same system. Each of these methods has strengths and blind spots. Radial velocity is powerful but favors large, close-orbiting planets. Transit photometry requires the planet's orbit to be aligned with our line of sight, which is not the case for most planetary systems. Gravitational microlensing events are brief and unrepeatable. Together, however, they have transformed our understanding of the galaxy. Before 1992, the number of confirmed planets beyond our solar system was 0. Today, it numbers in the thousands, and that figure continues to grow as instruments improve and observation campaigns accumulate more data. Understanding these methods also helps us understand the limits of what we know about specific planets. When astronomers report the discovery of a planet using radial velocity, they are measuring a minimum mass, not an exact one, because the measurement depends on the angle of the orbit relative to our line of sight. When transit photometry is used, we learn the planet's size, but not its mass directly. Combining both methods gives a richer picture. But for many planets, including some of the worlds around Proxima Centauri, only one method has been successfully applied, which means our knowledge remains partial. That is not a flaw in the science. It is an honest reflection of the difficulty of the task. Chapter 5. Proxima b, the nearest world. The search for planets around Proxima Centauri had been underway for years before any were confirmed. Astronomers suspected that planets might be there, partly because planets are now understood to be common around most types of stars, and partly because Proxima Centauri, as the nearest star to the Sun, was simply too important a target to leave unstudied. The technical challenge was significant. Proxima is an active star, and its flares and surface activity produce signals that can mimic or obscure the subtle signatures of an orbiting planet. Separating genuine planetary signals from stellar noise required careful, sustained observation. The breakthrough came through a coordinated international effort. In January of 2016, an observing campaign called the Pale Red Dot Project was launched, bringing together data from multiple ground-based telescopes with the specific aim of determining whether a suspected planetary signal around Proxima Centauri was real. The name was a quiet tribute to the famous description of Earth as a pale blue dot seen from the edge of the solar system. Here the dot would be paler still and red, seen from the surface of a world orbiting a dim red star. By August of 2016, the team was ready to announce their findings. A planet had been confirmed. It was designated Proxima Centauri b, and its existence was established through radial velocity measurements, showing a clear and repeatable wobble in the star's motion, with a period of approximately 11.2 Earth days. That period corresponded to the time it takes the planet to complete one orbit around its star. The orbital distance implied by that period is striking. Proxima b orbits its star at roughly 5% of the distance between Earth and the Sun. In our own solar system, that would place it far inside the orbit of Mercury, baking at temperatures that would make it completely uninhabitable. But Proxima Centauri is not our Sun. It is far dimmer. At that close distance, the amount of energy Proxima b receives from its star is estimated to be broadly comparable to the energy Earth receives from the Sun, which places the planet within what astronomers call the habitable zone, the region where surface temperatures could, under the right conditions, allow liquid water to exist. In terms of size, Proxima b is estimated to have a mass of at least 1.07 times that of Earth, making it a roughly Earth-sized world. This was immediately significant. The nearest star to our Sun appeared to host a planet of roughly Earth-like mass, sitting within its habitable zone. The discovery attracted enormous attention, not only within astronomy, but in the broader scientific and public conversation about life beyond Earth. But the discovery also came with important qualifications, and those qualifications matter. The radial velocity method gives us the planet's orbital period and a minimum mass. It does not tell us whether the planet has an atmosphere, what its surface is like, whether water exists there in any form, or whether the conditions are anything like those on Earth. These are not small gaps in knowledge. They are fundamental unknowns that the discovery of Proxima b opened rather than closed. One significant uncertainty concerns the planet's likely rotation. At such a close orbital distance, gravitational forces from the star are expected to have locked the planet's rotation to its orbital period, a state called tidal locking. A tidally locked planet keeps one face permanently turned toward its star, while the other faces permanently away. This creates a permanent day side and a permanent night side, with a narrow band of twilight running around the planet's edge. The implications for climate, atmospheric circulation, and surface conditions are profound and still debated among researchers. Some models suggest that a thick enough atmosphere could redistribute heat sufficiently to prevent the night side from freezing solid. Others suggest the atmospheric dynamics under such conditions would be deeply unfamiliar. Without direct observation of the planet's atmosphere, we cannot know which picture is closer to reality. Another major uncertainty concerns the atmosphere itself. Whether Proxima b has retained any atmosphere at all is an open question. The intense radiation environment created by Proxima Centauri's flares, sustained over billions of years, could have eroded an atmosphere entirely, particularly if the planet lacks a strong magnetic field to deflect charged particles. Without an atmosphere, there is no surface pressure to keep water liquid, no protection from radiation, and no mechanism for the kind of climate regulation that Earth's atmosphere provides. These are not hypothetical concerns. They represent genuine physical processes that operate on planets orbiting active stars, and they make the habitability of Proxima b deeply uncertain, despite its location within the habitable zone. What we can say with confidence is that Proxima b exists, that it is roughly Earth-sized, and that it orbits within the distance at which a planet could in principle maintain liquid water on its surface if conditions are favorable. That is a meaningful set of facts. It establishes Proxima b as a world worth continued study, and it makes the Proxima Centauri system a priority target for future instruments capable of probing planetary atmospheres at this distance. What it does not do, and what it was never intended to do, is settle the question of life. That question remains open, as it should. Chapter 6. The Habitability Question. The phrase habitable zone has a way of carrying more weight than it should. When astronomers say a planet sits within the habitable zone of its star, they mean something specific and relatively narrow. The range of orbital distances at which the planet receives enough stellar energy for liquid water to exist on its surface, assuming the planet has an atmosphere of roughly Earth-like composition. That is the entirety of what the term technically implies. It says nothing about whether the planet actually has an atmosphere. It says nothing about the planet's geology, its magnetic field, its rotational state, its chemical composition, or its history. It is a first filter, not a final verdict. This distinction matters enormously when we discuss planets like Proxima b, because the habitable zone location is often the first fact reported and the last one examined critically. A planet in the habitable zone sounds promising, and it may indeed be promising. But the full picture of what makes a world genuinely capable of supporting life, or at least of maintaining conditions broadly similar to those on Earth, involves a much longer list of requirements. Start with the atmosphere. An atmosphere serves multiple functions that are essential for the kind of surface environment we associate with habitability. It regulates temperature by trapping heat and distributing it across the planet's surface. It provides the pressure necessary to keep water in liquid form, rather than boiling away into space or freezing solid. It shields the surface from harmful radiation, particularly the high-energy ultraviolet and X-ray radiation that stars emit in varying quantities. And it acts as a reservoir for the chemical elements and compounds that biology relies on. A planet without an atmosphere, or with an atmosphere radically different from Earth's in composition or density, faces immediate challenges on all of these fronts. For a planet orbiting Proxima Centauri, atmospheric retention is one of the most pressing concerns. The star's flare activity bombards any nearby planet with high-energy radiation and charged particles. These particles interact with the upper layers of a planetary atmosphere and can gradually strip it away over time, a process called atmospheric sputtering. Whether Proxima b has retained an atmosphere depends on several factors we do not currently know. The planet's initial atmospheric mass, the rate at which it outgassed material from its interior over geological time, and critically, whether it possesses a magnetic field strong enough to deflect charged particles before they reach the upper atmosphere. On Earth, the magnetic field generated by the churning of liquid iron in our planet's outer core plays a vital role in protecting the atmosphere from solar wind erosion. Mars, which lost much of its magnetic field billions of years ago, also lost the majority of its atmosphere over the same period. The connection is not coincidental. For Proxima b, whether a significant magnetic field exists depends partly on the planet's interior structure and thermal history, and partly on its rotational dynamics. A tidally locked planet rotates very slowly relative to a non-locked one, and some models suggest that slow rotation reduces the efficiency of the dynamo effect that generates a magnetic field. Other models suggest that different mechanisms could still produce a meaningful field under tidal locking. This remains an active area of research. Tidal locking itself introduces another layer of complexity. The permanent day side of a tidally locked planet receives continuous stellar radiation and would likely be very warm, potentially extremely warm, depending on the atmosphere's composition and thickness. The permanent night side receives no direct stellar energy and could be extremely cold, potentially cold enough to freeze atmospheric gases against the surface. Between these extremes lies the terminator, the boundary between perpetual day and perpetual night, which might offer more moderate temperatures. But whether the atmosphere circulates efficiently enough to spread heat from the day side to the night side and prevent catastrophic freeze-out on the dark hemisphere depends on atmospheric thickness, composition, and circulation dynamics that we cannot currently measure at Proxima's distance. Radiation exposure adds yet another dimension. Even setting aside flares, the baseline ultraviolet output of Proxima Centauri is higher relative to its total luminosity than that of our Sun. A planet in the habitable zone would receive significantly more ultraviolet radiation per unit of total energy than Earth does, even during the quiet periods between flares. Ultraviolet radiation can break apart atmospheric molecules, drive chemical reactions that alter atmospheric composition, and damage biological molecules directly. On Earth, the ozone layer absorbs the majority of the sun's ultraviolet output before it reaches the surface. Whether a planet like Proxima b could maintain an equivalent protective layer under the radiation conditions it experiences is uncertain. None of this is intended to conclude that Proxima b is uninhabitable. It is intended to illustrate why the habitable zone designation is a beginning rather than an answer. The zone tells us where to look. It does not tell us what we will find when we look more carefully. A genuinely habitable world requires not just the right distance from its star, but the right atmosphere, the right geology, the right magnetic environment, and sufficient time for whatever processes produce complexity to operate without being repeatedly disrupted. These are demanding requirements, and meeting all of them simultaneously appears to require a particular combination of circumstances that we are only beginning to understand. Chapter 7. Red Dwarfs and the Fate of Atmospheres. The question of whether a planet can hold onto its atmosphere is one of the most consequential in all of planetary science. An atmosphere is not a permanent feature of a world. It is a dynamic system, continuously gained and continuously lost, maintained only as long as the processes that replenish it outpace the processes that strip it away. For planets orbiting red dwarf stars, the balance between those competing processes is particularly precarious, and understanding why requires looking at what atmospheres are made of, where they come from, and what forces work against them. Planetary atmospheres have several sources. The most significant for rocky planets is outgassing from the interior. As a planet forms and its interior heats up through the decay of radioactive elements and the energy released by gravitational compression, volatile compounds trapped in the rock are released and rise to the surface. Water vapor, carbon dioxide, nitrogen, sulfur compounds. These are the raw materials from which early atmospheres are assembled. Over geological time, continued volcanic activity replenishes the atmosphere from below, maintaining a supply of gases even as some are lost from above. Loss from above is driven primarily by the star. Stars emit not only visible light, but a continuous stream of charged particles, the stellar wind, and periodic bursts of much more intense radiation and particle flux during flares and coronal mass ejections. When these particles reach a planet, they interact with the upper atmosphere. High-energy photons can ionize atmospheric molecules, giving them enough energy to escape the planet's gravity entirely. Charged particles from the stellar wind can physically collide with atmospheric particles and knock them into space, a process called sputtering. Over millions and billions of years, these losses accumulate. Whether a planet loses its atmosphere faster than it can replenish it depends on several factors. The mass of the planet determines how strongly gravity holds the atmosphere in place. Larger planets with stronger gravity retain atmospheres more easily than smaller ones. The composition of the atmosphere matters too, because lighter molecules like hydrogen and helium are more easily lost than heavier ones. And critically, the presence or absence of a planetary magnetic field makes an enormous difference. A strong magnetic field deflects the charged particles of the stellar wind before they reach the upper atmosphere, providing a protective envelope that significantly reduces the rate of atmospheric loss. Mars offers a compelling case study. Early in its history, Mars appears to have had a thicker atmosphere, liquid water on its surface, and conditions that may have been broadly habitable. The evidence for this is written in the geology. Ancient river channels, lake beds, and mineral deposits that form only in the presence of liquid water. But Mars is a small planet, and its interior cooled relatively quickly. As the interior cooled, the convective churning of liquid metal in the core slowed, and the magnetic field it generated weakened and eventually largely disappeared. Without that magnetic shield, the Martian atmosphere was exposed directly to the solar wind. Over hundreds of millions of years, it was gradually stripped away. Today, the Martian atmosphere is less than 1% as dense as Earth's, and the surface is cold, dry, and bathed in radiation. The parallel to planets orbiting red dwarf stars is instructive but not exact. Red dwarfs are far more active than our Sun, particularly in their youth. The stellar wind from a young red dwarf is significantly more intense than the solar wind Earth has experienced throughout its history, and the frequency and intensity of flares is considerably higher. A planet forming around a young red dwarf would be subjected to an extremely energetic radiation environment during the very period when it is assembling its initial atmosphere. Whether that atmosphere survives depends on how quickly the planet can outgas material from its interior to replace what is lost, and whether its magnetic field is strong enough to provide meaningful protection. The magnetic field question is particularly complex for planets around red dwarfs because of tidal locking. As we discussed earlier, planets in the habitable zones of red dwarfs are expected to be tidally locked, rotating once per orbit, rather than spinning freely. The generation of a planetary magnetic field through the dynamo effect depends on a combination of a liquid conducting interior and rotation. A tidally locked planet rotates much more slowly than a freely spinning one, which may reduce the efficiency of the dynamo and produce a weaker magnetic field. Some models suggest that tidal locking essentially eliminates the possibility of a significant magnetic field for planets in this situation. Other models propose alternative dynamo mechanisms that could still operate under slow rotation. The theoretical picture is genuinely unsettled. What is clear is that the atmospheric survival of planets around red dwarfs cannot be assumed. It must be demonstrated, and demonstrating it requires either direct atmospheric detection through spectroscopy or sufficiently detailed knowledge of the planet's interior and magnetic state to model the atmospheric evolution reliably. Neither is currently achievable for Proxima b with existing instruments. The James Webb Space Telescope may be able to place constraints on the presence or absence of a substantial atmosphere around Proxima b through careful observation of its thermal emission. But this is a difficult measurement, and the results are likely to be ambiguous rather than definitive in the near term. This uncertainty is not a reason for pessimism. It is a reason for continued investment in the instruments and techniques that can resolve it. The fate of atmospheres around red dwarf planets is one of the central open questions in exoplanet science, and answering it will require both better observations and better theoretical models of how planetary interiors, magnetic fields, and stellar environments interact over geological timescales. The nearest red dwarf planet, Proxima b, sits at the center of that question, making it not just an interesting world in its own right, but a critical test case for an entire class of planets that make up a substantial fraction of all potentially habitable worlds in the galaxy. Chapter 8. Proxima d, a technological milestone. 6 years after the announcement of Proxima b, a second planet in the system made headlines, though for reasons that were as much about engineering as they were about the planet itself. Proxima Centauri d was announced in February of 2022, and while it is a small and probably inhospitable world, its detection represented a significant achievement in the development of the instruments astronomers use to find planets. The story of Proxima d begins in 2020, when a faint signal appeared in radial velocity data being collected as part of an ongoing study of Proxima Centauri. The signal had a period of approximately 5.1 days, suggesting an object completing a very fast orbit around the star. But the signal was extremely weak, right at the edge of what the instruments could reliably detect. It took additional observation campaigns and careful analysis to build sufficient confidence that the signal was real and was caused by a planet rather than by some form of stellar activity or instrumental artifact. When the discovery was confirmed, the properties of Proxima d turned out to be quite different from those of Proxima b. The planet has a mass of at least approximately 1/4 that of Earth, placing it in a category called sub-Earth planets. It orbits Proxima Centauri at a distance of only about 4.3 million kilometers, which is closer to the star than Proxima b, and far inside what would be considered the habitable zone. At that distance, the equilibrium temperature of the planet's surface would be very high, in the range of 87 degrees Celsius or above, making it too hot to sustain liquid water under any plausible atmospheric scenario. Proxima d is almost certainly not a habitable world, but what made the discovery significant was not the planet's habitability. It was the fact that it had been detected at all. Prior to Proxima d, the radial velocity method had never been used to confirm a planet this small. The wobble that a sub-Earth mass planet induces in its host star is extraordinarily subtle, amounting to a velocity change of less than a meter per second in the star's motion. Detecting that signal, isolating it from the noise of the star's own activity, and confirming it with sufficient statistical certainty required instruments of remarkable precision. The spectrograph used to make these measurements, Espresso, installed at the Very Large Telescope facility in Chile, represents one of the most sensitive instruments of its kind ever built. Its ability to detect the minute shifts in stellar spectra required to confirm Proxima d pushed the boundaries of what ground-based astronomy can achieve. In doing so, it demonstrated that sub-Earth mass planets are within reach of radial velocity detection, opening the door to finding smaller and potentially more Earth-like worlds around nearby stars in future observations. Proxima d also adds to the portrait of the Proxima Centauri system as a place of genuine complexity. Rather than a single planet in a quiet orbit, the system contains at least 2 confirmed worlds and a third candidate, arranged at very different distances from their star and representing very different physical types. This layered structure is not surprising in the context of what we now know about planetary systems generally. Our own solar system contains 8 planets of dramatically different types, arranged across a wide range of orbital distances. Other systems studied in detail often reveal similar complexity, but each new world added to the Proxima catalogue deepens our understanding of what the nearest stellar neighborhood actually looks like. Chapter 9. Proxima c, an open question. Not every claimed planetary discovery reaches a clean resolution. Science moves through stages of evidence, and sometimes the evidence for a particular claim remains genuinely ambiguous for years, or even indefinitely. Proxima Centauri c occupies exactly this uncertain territory. It is a planet that may exist, whose detection has been claimed and contested, and whose status remains unresolved in the current literature. The first indications of Proxima c emerged in 2019, again through radial velocity measurements. The signal, if real, pointed to a planet with a mass several times that of Earth, orbiting Proxima Centauri at a distance that would give it an orbital period of approximately 1,928 days, or roughly 5¼ Earth years. That orbital distance would place it far outside the habitable zone, in a region far colder than the zone where liquid water could exist. In 2020, additional support for the existence of Proxima C appeared to come from an independent source. Researchers analyzing data from the Hubble Space Telescope using a technique called astrometry, which involves measuring the precise position of a star over time and looking for tiny positional shifts caused by a companion's gravitational pull, reported that the data was consistent with the existence of Proxima C. This seemed to strengthen the case for the planet's reality, drawing on a completely different measurement method from the radial velocity data that had first suggested it. However, in 2022, the picture became more complicated. A separate team of researchers reanalyzed the original radial velocity data and concluded that the signal attributed to Proxima C could instead be explained by small systematic errors in the way the data had been processed, rather than by the gravitational influence of a planet. This type of challenge is not unusual in exoplanet science. Disentangling genuine planetary signals from instrumental artifacts and stellar noise is technically demanding, and it is not always possible to do so definitively with a single dataset. The difficulty with Proxima C, compared to Proxima B and D, is that its proposed orbit is very long and slow. Confirming a planet through radial velocity generally becomes easier when more complete orbital cycles have been observed, because the repeating pattern of the signal becomes clearer over time. For a planet with a nearly 5-year orbit, accumulating enough data to confidently distinguish a real signal from noise takes considerably longer than for a planet with an 11-day or 5-day orbit. The current dataset does not yet provide the coverage needed to settle the question. What makes the case of Proxima C particularly interesting is what it would imply if the planet does exist. A planet of several Earth masses orbiting at that distance from a low luminosity red dwarf would be a cold and dark world, receiving very little stellar energy. Its surface temperatures would be far below freezing under any plausible atmospheric scenario. It would almost certainly not be habitable in any conventional sense, but its existence would tell us something important about the architecture of the Proxima system and about the processes by which planets form around red dwarf stars. A planet forming at that distance from such a dim star would have done so under very different conditions from any world in our own solar system. For now, Proxima C sits in the category of unconfirmed candidates. It may be confirmed by future observations, or future data may conclusively rule it out. In the meantime, its uncertain status is a useful reminder that planetary science is an ongoing process of evidence accumulation, not a series of sudden revelations. The nearest star system has not finished revealing itself. Chapter 10. Rogue Planets and Jumbos. So far, we have been thinking about planets in a familiar context. Worlds orbiting stars, receiving light and energy from a central sun, defined by their relationship to the stellar body around which they travel. But not all planets live this way. Some planets, perhaps a very large number of them, drift through interstellar space entirely alone, unbound to any star, wandering through the darkness between stellar systems. These are called rogue planets, and their existence raises interesting questions about how planets form and about the diversity of environments in which planetary mass objects can exist. Rogue planets were theorized long before they were confirmed. The logic behind their existence is straightforward. The early histories of planetary systems are chaotic. Planets form from swirling disks of gas and dust around young stars, and in the process of forming, they interact gravitationally with each other and with the star. These interactions, can be violent enough to eject a planet entirely from the system, sending it off into interstellar space on a trajectory that takes it away from its birth star forever. Given the number of planetary systems in the galaxy and the frequency with which such ejections are thought to occur, the total population of rogue planets could be very large. Some estimates suggest there may be more rogue planets drifting through the Milky Way than there are planets orbiting stars. Direct detection of rogue planets is technically challenging, for obvious reasons. A planet produces no significant light of its own, and without a star to orbit, the detection methods that rely on planetary transits or stellar wobbles do not apply. Gravitational microlensing, which detects the brief brightening of a background star caused by a massive foreground object bending its light, has been used to find rogue planet candidates. But microlensing events are brief and unrepeatable, making follow-up observations impossible and leaving significant uncertainty about the individual objects detected. The picture became considerably more interesting in late 2023, when the James Webb Space Telescope turned its instruments on the Orion Nebula and conducted a systematic survey of the region. Among the results was a striking discovery. Not only were there numerous free-floating planetary mass objects in the nebula, but a significant fraction of them appeared to be traveling in pairs, orbiting each other with no star in sight. These paired objects were given the informal designation jumbos for Jupiter mass binary objects because their masses are in the range of Jupiter's mass and they exist in binary configurations. The existence of jumbos was unexpected. Binary configurations are common among stars and become progressively less common as the mass of the objects decreases. Brown dwarfs, which are objects too massive to be planets but too small to sustain full stellar nuclear fusion, can sometimes be found in binaries, though less frequently than stars. But objects in the mass range of Jupiter, forming binary pairs in interstellar space, had not been predicted by existing models of planet formation. Roughly 9% of the free-floating planetary mass objects Webb observed in the Orion region appeared to be in these binary arrangements, a fraction that is strikingly high given theoretical expectations. Two broad explanations have been proposed. The first is that jumbos are planets that were ejected from forming planetary systems, and that in some cases two planets were ejected simultaneously in the same direction with similar velocities, allowing gravity to bind them into a pair once they were free of their birth star. This is mechanically possible, but requires a combination of circumstances that seems improbable at the frequency observed. Ejecting two Jupiter mass planets in the same direction at the same speed, close enough that they then settle into a mutual orbit, is not impossible, but models of planetary ejection do not naturally predict it happening at a rate of nearly 1 in 10. The second explanation is that jumbos form directly from interstellar material, in a process similar to the way stars form, but at a much smaller scale. The difficulty here involves a concept called the opacity limit for fragmentation. When gas collapses under gravity to form a star, the collapsing material heats up as it becomes denser, and eventually the heat builds fast enough to resist further collapse below a certain mass scale. This sets a lower limit on the mass of objects that can form spontaneously from collapsing interstellar gas, and that limit is generally thought to be in the range of brown dwarf masses, considerably larger than a Jupiter mass object. Forming a Jupiter mass planet directly from interstellar gas without a protoplanetary disk would require overcoming or circumventing this limit in some way. Some researchers have proposed that magnetic fields in the collapsing gas cloud could play a role, providing an additional mechanism that allows smaller objects to form independently. This idea is speculative, and the observational evidence needed to test it is not yet available. What the discovery of jumbos has established clearly is that existing models of how planets and stars form are incomplete. The universe appears to be producing planetary mass binary objects in interstellar space at a rate that our current understanding cannot adequately explain. That is not a failure of science. It is one of science's most valuable outcomes, a discovery that reveals the limits of existing knowledge and points toward the questions that need to be asked next. Chapter 11. The Search Across the Galaxy. The story of how humanity came to understand the abundance of planets in the galaxy is relatively recent, and it unfolded with a speed that surprised even many of the scientists involved. For most of astronomical history, the existence of planets around other stars was a reasonable assumption, but an unverified one. The technical barriers to detection were formidable. It was not until 1992 that the first confirmed exoplanets were announced, and those first discoveries orbited a pulsar, a rapidly spinning stellar remnant, rather than a sun-like star. The first planet confirmed around a main sequence star similar to our Sun, followed in 1995. From that starting point, the field expanded rapidly. Ground-based observatories developed increasingly sensitive spectrographs capable of detecting the small radial velocity signals of orbiting planets. Space-based missions removed the distorting effects of Earth's atmosphere and enabled continuous, uninterrupted monitoring of large numbers of stars. Each advance in instrumentation brought new discoveries, and each new discovery refined the picture of how common planets actually are. The Kepler Space Telescope, launched in 2009, was transformative. Its mission was to monitor the brightness of approximately 150,000 stars in a fixed patch of sky, looking for the periodic dimmings caused by planets passing in front of their host stars. Over its operational lifetime, Kepler confirmed the existence of thousands of planets and identified thousands more candidates awaiting confirmation. The sheer scale of its findings made something clear that had been suspected but not established. Planets are not rare. They are the default outcome of star formation. Most stars have planets. Many stars have multiple planets. The galaxy contains more planetary systems than anyone had dared to assume. Among Kepler's most significant contributions was the characterization of planetary sizes across the detected population. The mission found planets of all sizes, from objects larger than Jupiter down to worlds smaller than Earth. It found planets in tight orbits around their stars, completing circuits in just a few days, and planets in wider orbits taking years. It found planets around stars of different types and ages. This diversity established that planet formation is not a precise or narrowly constrained process. It produces an enormous variety of outcomes across an enormous range of stellar environments. Following Kepler, the TESS mission, the Transiting Exoplanet Survey satellite, extended the search to a much larger fraction of the sky, covering a field roughly 400 times larger than Kepler's. TESS was designed to find planets around stars close enough to Earth for follow-up characterization to be feasible, making it particularly valuable for identifying targets for atmospheric study with instruments like the James Webb Space Telescope. Together, Kepler and TESS have provided a statistical foundation for understanding how many planets exist in the galaxy and what types of orbits and sizes are most common. The Cheops mission, launched by the European Space Agency in 2019, approached the problem from a different angle. Rather than discovering new planets by surveying large numbers of stars, Cheops was designed to study known exoplanets in greater detail, using extremely precise photometry to refine measurements of their sizes and to study their phase curves, the variation in reflected light as they move through their orbits. This kind of detailed characterization is essential for understanding individual worlds more deeply, distinguishing between different possible interior compositions and identifying candidates for atmospheric study. The James Webb Space Telescope, with its unprecedented sensitivity at infrared wavelengths, has opened a new era in exoplanet atmospheric characterization. By analyzing the spectral fingerprint of starlight filtered through a planetary atmosphere during transit, Webb can identify specific molecules present in that atmosphere. Early results from the mission have already demonstrated the detection of carbon dioxide, water vapor, sulfur dioxide, and other molecules in the atmospheres of exoplanets, marking the beginning of a transition from simply finding planets to understanding what they are actually made of. This progression from discovery to characterization is one of the defining shifts in exoplanet science in the current decade. The first era of the field was defined by abundance. How many planets are there and where are they? The emerging era is defined by quality. What are these planets actually like, and which of them might be capable of supporting life? The tools now being deployed and the ones being planned are increasingly oriented toward answering that second set of questions. Chapter 12. The Architecture of Other Solar Systems. Before the era of exoplanet discovery, the solar system was our only detailed example of how planets arrange themselves around a star. And for a long time, it seemed reasonable to assume that other planetary systems, if they existed, would be broadly similar in their organization. Perhaps they would have small rocky planets in the inner regions, large gas giants farther out, and a structured, orderly progression from one type to the other. Perhaps the architecture of our solar system reflected something fundamental about how planets form and where they end up. The discoveries of the past 3 decades have thoroughly dismantled that assumption. The galaxy contains planetary systems of extraordinary diversity, arranged in configurations that our solar system gives no hint of. Understanding that diversity is important for placing the Alpha Centauri system in context, and for appreciating what the architecture of a planetary system can tell us about its history. One of the earliest and most surprising findings of the exoplanet era was the existence of hot Jupiters. These are gas giant planets, similar in mass and composition to Jupiter, but orbiting their stars at distances of only a few % of an astronomical unit, completing full orbits in just a few days. In our solar system, Jupiter sits at 5 astronomical units from the Sun, far out in the cold outer regions. The idea that a planet of similar mass could orbit 100 times closer to its star, in scorching proximity to an intensely radiating surface, was not predicted. And yet, hot Jupiters turned out to be common enough that they were among the first exoplanets discovered, precisely because their large mass and close orbit produce the strongest and most detectable radial velocity signals. The explanation that eventually emerged for hot Jupiters involves planetary migration. Gas giants form in the cold outer regions of a protoplanetary disk, where ice and other volatile materials can condense and contribute to a forming planet's growth. But as they grow, they interact gravitationally with the disk itself, and those interactions can cause the planet to spiral inward toward the star over time. If the disk dissipates before the planet has migrated all the way to a very close orbit, it stops somewhere in the middle. If the disk persists long enough, the planet can end up at an extremely close orbital distance, becoming a hot Jupiter. This migration process reshapes the entire inner planetary system as the giant planet moves through it, sweeping up or ejecting smaller planets that would otherwise occupy the inner orbits. The Kepler mission revealed another surprising architectural feature: the prevalence of compact multi-planet systems. Many of the planetary systems Kepler found contain multiple planets packed into orbits much closer to their stars than any of the planets in our solar system, with orbital periods of days to weeks rather than months or years. In some of these systems, several planets orbit within a distance that would fit comfortably inside Mercury's orbit in our solar system. These compact systems are often in or near orbital resonance, meaning the orbital periods of adjacent planets form simple ratios like 2:1 or 3:2, a configuration that arises naturally when planets have migrated and settled into stable gravitational arrangements. The Alpha Centauri system, and Proxima Centauri in particular, fits partially into this pattern. Proxima b and d both orbit at very close distances to their star, with orbital periods of 11 and 5 days respectively. If Proxima c exists at its proposed 5-year orbit, the system would span a much wider range of distances, but the inner two planets are consistent with the compact architecture seen in many other red dwarf systems. Red dwarfs appear to commonly host closely packed inner planetary systems, which makes sense given the small size of the habitable zone and the prevalence of short-period planets in the observed population. What the diversity of planetary system architectures tells us, at a fundamental level, is that the process of planet formation is sensitive to initial conditions in ways that produce very different outcomes. The mass of the protoplanetary disk, the abundance of different chemical elements, the presence or absence of giant planet formation, the timing of disk dissipation, gravitational interactions with passing stars. All of these factors can tip a forming planetary system toward one configuration or another. Our solar system, with its relatively clear separation between inner rocky planets and outer gas giants, and its relative absence of planets on very tight orbits, may be somewhat unusual in the broader context of what the galaxy produces. Understanding this diversity is not merely an exercise in cataloging variation. It has direct implications for habitability. A planetary system's architecture determines the dynamical environment in which each planet exists. A tightly packed system of small planets may be stable over long timescales, or it may be prone to gravitational perturbations that gradually alter planetary orbits in ways that push worlds out of habitable zones or trigger orbital instabilities. The presence of a giant planet in the outer system can provide stability by preventing other objects from perturbing inner planets, as Jupiter is thought to do for Earth to some degree, or it can introduce chaos by flinging objects onto crossing orbits. The history of a planetary system is written partly in the architecture it has settled into, and reading that history requires understanding the full range of architectures the galaxy produces. Chapter 13. What makes a world truly habitable? We have touched on the concept of habitability at several points already, but it is worth addressing it directly and in some depth, because it is one of the most genuinely complex questions in contemporary science, and one that is often simplified in ways that obscure its real difficulty. At its most basic, habitability refers to the capacity of an environment to support life. But that definition immediately raises a further question. What kind of life? The only life we know with certainty exists is life on Earth, and Earth life operates within a specific set of chemical and physical parameters. It requires liquid water as a solvent. It relies on carbon-based chemistry. It needs access to energy, whether from sunlight or from chemical gradients. It requires protection from radiation intense enough to break apart biological molecules. and it needs the conditions that allow these requirements to be met to persist over timescales long enough for biological complexity to develop. These requirements, taken together, constitute a fairly demanding set of conditions. Liquid water requires temperatures between 0 and 100 degrees Celsius at standard atmospheric pressure, and requires that atmospheric pressure to exist. Carbon chemistry in the forms relevant to biology requires a range of elements, including carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, to be present and chemically accessible. Energy availability requires either a stable radiative source or a chemically active environment. Radiation protection requires either an atmosphere with appropriate absorbing layers, a magnetic field, or sufficient depth of water or rock to provide shielding. Meeting all of these requirements simultaneously on a planetary surface for billions of years turns out to be quite demanding. Earth meets all of them, and it has done so continuously for most of its history. But Earth's success in this regard is the product of many interacting factors: its distance from a relatively stable star, its magnetic field generated by an active interior, its plate tectonics which recycle carbon and maintain a long-term climate thermostat, its large moon which stabilizes its axial tilt and prevents extreme climatic oscillations, its atmospheric composition maintained by the interplay of geology and biology, and its position within the solar system, shielded from some categories of bombardment by the gravitational influence of the outer planets. How many of these factors are strictly necessary, and how many represent contingent features of Earth's particular history, is not known. Astrobiology, the study of life's potential beyond Earth, grapples with exactly this question. Some researchers argue that many of Earth's specific features, including the large moon and plate tectonics, are important contributors to long-term habitability. Others argue that life is adaptable enough to emerge and persist under a much wider range of conditions, and that some of what seems necessary from our single example is in fact merely familiar. What is becoming clear as the exoplanet catalogue grows and our ability to characterize individual worlds improves is that planets meeting even a subset of the familiar habitability criteria are less common than the raw number of planets in the galaxy might suggest. Rocky planets in the habitable zone exist, but the fraction that also have the right atmospheric composition, the right interior activity, and the right stellar environment is smaller. The fraction that maintain all of those conditions over geological timescales is smaller still. Earth, seen in this light, is not simply one of countless identical copies scattered across the galaxy. It is the outcome of a particular combination of conditions that, while not vanishingly rare, may not be nearly as common as early optimism about exoplanet abundance implied. This does not mean life is rare. Biology may find ways to operate in environments quite different from Earth's surface. Subsurface oceans, like those suspected beneath the ice of Jupiter's moon Europa and Saturn's moon Enceladus, might support life without any of the surface conditions we associate with habitability. Chemistry-driven life in environments without sunlight, without oxygen, at extreme temperatures or pressures, has been discovered on Earth itself, in hydrothermal vents and deep rock formations and highly acidic or saline lakes. The range of conditions that biology can tolerate on Earth is already much wider than would have been guessed before these environments were explored. Extrapolating to other worlds, the range of potentially habitable environments may be considerably broader than the simple habitable zone model implies. But broadening the definition of habitability also means loosening the criteria by which we identify candidates from a distance. We can measure orbital distances from spectra and brightness measurements. We cannot yet peer beneath the ice of a distant ocean moon. The practical question for astronomy is not the full theoretical range of habitable environments, but the subset we can actually detect and characterize with current and near-future technology. And in that more constrained sense, the picture of a galaxy full of easily habitable worlds has been substantially revised since the early days of exoplanet discovery. Chapter 14. The Scale of the Search. There is a particular kind of perspective that astronomy offers, which is unlike anything available in ordinary experience. It involves holding very large numbers and very vast distances in mind simultaneously, not with anxiety or overwhelm, but with a kind of quiet appreciation for the scale of what exists. This chapter is an invitation to do exactly that, to sit for a moment with the numbers that frame the search for life beyond Earth, and to consider what they actually mean. The Milky Way galaxy contains somewhere between 200 billion and 400 billion stars. That range itself reflects genuine uncertainty. Counting stars in a galaxy is not straightforward, and different methods and assumptions produce different estimates. But even the lower bound is a number that resists easy comprehension. 200 billion is 200,000 million. If you were to count stars at a rate of 1 per second, without stopping, it would take over 6,000 years to count 200 billion of them. Of those stars, current evidence suggests that the majority host at least one planet. Some host many. The total planetary population of the Milky Way, by these estimates, likely runs to the trillions, not billions, trillions. The scale of the raw material available for producing worlds of any kind is staggering. Within that population, the fraction of planets that are roughly rocky and roughly Earth-sized, rather than gas giants or ice giants or other configurations, is significant but not dominant. Rocky planets appear to be common around many types of stars, but they represent one subset of a diverse planetary population. Among rocky planets, the fraction that orbit within the habitable zone of their star, where temperatures could in principle allow liquid water on a surface with the right atmosphere, is estimated to be meaningful but not universal. Depending on the assumptions used and the type of star considered, estimates range from a few percent to a few tens of percent of rocky planets sitting within the habitable zone. Even at the more conservative end of those estimates, the resulting number of potentially habitable rocky planets in the Milky Way is in the billions. Billions of worlds sitting at the right distance from their stars to potentially maintain liquid water. That is an astonishing number, and it is worth letting it settle for a moment. The galaxy is not a barren place. It is, if current understanding is correct, filled with candidates. But candidates are not inhabitants, and this is where the scale of the search runs into the scale of our ignorance. Of those billions of candidate worlds, we have currently characterized the atmospheres of only a handful of planets, and none of those are small rocky worlds in the habitable zone of a sun-like star. We have detected molecules in the atmospheres of larger, hotter planets that are far easier to study. We have placed constraints on the atmospheres of a small number of rocky planets. But the specific measurement we most want to make, the spectral analysis of a genuinely Earth-like planet's atmosphere around a star similar to our Sun, looking for the combination of gases that would suggest active biology, remains beyond our current capabilities. This is changing. The James Webb Space Telescope has demonstrated that atmospheric characterization of small planets is possible, at least for planets orbiting small, nearby stars where the geometry is favorable. Future planned observatories, including large space telescopes optimized for direct imaging of Earth-like planets around Sun-like stars, aim to make this measurement routine. The timescale for those missions is measured in decades, but the direction is clear. There is a useful way to think about where we are in this search. Imagine that the full investigation of life beyond Earth is a journey of 1,000 steps. The first step was establishing that planets exist beyond our solar system, accomplished in the 1990s. The next several steps involved demonstrating that planets are common, that rocky planets exist, that some orbit in habitable zones. Those steps have been taken. We are perhaps 50 or 100 steps into a 1,000-step journey. The destination is not visible yet. The path ahead is long. But the early steps have confirmed that we are moving in a direction that makes sense, toward a galaxy that genuinely contains the raw material of what we are looking for. The nearest planets to our solar system sit very close to the beginning of that path. They are the first waypoints, the first specific addresses we can point to and say, there are worlds there. We do not yet know what those worlds are really like. We do not know if they are silent and barren or rich with chemistry. We do not know if they are the first in a long list of habitable places we will eventually compile, or if they will turn out to illustrate how demanding the conditions for life really are. Both outcomes would be profound. Both would advance the journey. And either way, the search continues, step by patient step, into the vast and populated dark. Chapter 15. Reaching the nearest worlds. Everything we have discussed so far involves observing the nearest planetary systems from a distance. We detect planets through the effects they have on their stars. We study their atmospheres by analyzing light that has passed through them. We build detailed pictures of worlds we have never visited and may never visit, using data collected from instruments millions of kilometers away. This is a remarkable achievement, and it will continue to yield important knowledge. But there is a separate question that the proximity of the Alpha Centauri system makes feel, if not urgent, at least conceivable. Could we ever go there? The honest answer is that with current technology, no. The fastest spacecraft humanity has ever launched, the Voyager probes, are moving at roughly 17 kilometers per second relative to the Sun. At that speed, reaching Proxima Centauri would take approximately 75,000 years. This is not a planning horizon any mission architect can work with. The distance is not merely large. It is categorically different from the distances involved in missions to the outer solar system, which already represent extraordinary feats of engineering and patience. But the question of whether interstellar travel is possible in principle, even if far beyond current capabilities, is a legitimate one, and it has attracted serious scientific attention. Several propulsion concepts have been explored that could theoretically reduce travel times to destinations like Alpha Centauri to something within a human lifetime, or at least within a few generations. One of the most discussed proposals is the Breakthrough Starshot Initiative, announced in 2016 and backed by investor Yuri Milner, along with a scientific advisory group. The concept involves sending not a conventional spacecraft, but extremely small, lightweight probes, essentially chip-scale devices mounted on a reflective sail, and accelerating them to a significant fraction of the speed of light using a powerful ground-based laser array. At 15 to 20% of the speed of light, such probes could reach the Alpha Centauri system in roughly 20 years. Another 4 years would then pass before any data transmitted by the probes arrived back on Earth. The engineering challenges involved are substantial. The laser array required would need to deliver power equivalent to a large number of nuclear power plants, focused precisely on a target that becomes smaller and more distant by the second. The probes themselves would need to survive acceleration forces that would destroy conventional electronics, the vacuum and radiation of interstellar space, and collisions with interstellar dust particles that, at those velocities, carry the energy of a bullet impact. The communication systems capable of transmitting data across 4 light-years from a gram-scale device do not yet exist. None of these problems are obviously insoluble, but none of them are trivial, and solving them would require advances across multiple fields of engineering and materials science. Other propulsion concepts have also been discussed, including nuclear pulse propulsion, which would use a series of nuclear explosions to accelerate a larger spacecraft, and solar sails powered by the pressure of sunlight from a close approach to the Sun. Each approach has its own profile of advantages and challenges. None is close to implementation. What the breakthrough starshot concept captures, even in its current speculative form, is something important about the relationship between proximity and possibility. The Alpha Centauri system is 4 light-years away. That is an enormous distance by any human measure. But it is not infinite. It is the nearest destination. And the fact that it contains planets, including at least one of roughly Earth-like mass sitting within its star's habitable zone, gives any future mission a purpose beyond mere exploration of stellar physics. It would be a journey to a planetary system, with worlds that can be examined up close in ways that no amount of remote observation can substitute for. Whether humanity will ever actually make such a journey, and on what timescale, is impossible to predict. But the fact that the question can be asked seriously, and that serious engineering proposals exist for at least a minimal version of such a mission, is itself a reflection of how much our understanding of the nearest stellar neighborhood has changed in just the past decade. Chapter 16. What the nearest planets teach us. The discoveries made in and around the Alpha Centauri system over the past decade have done something that goes beyond simply adding entries to a catalogue of exoplanets. They have forced a series of reckonings about what planets are, about what habitability means, about how common the conditions for life might be, and about what our own world represents in the broader context of the galaxy. Before Proxima b was confirmed in 2016, the nearest known planet beyond our solar system was considerably farther away. The discovery that the nearest star hosts at least one roughly Earth-sized planet in its habitable zone was a conceptual shift as much as a scientific one. It made the question of life beyond our solar system feel closer, not because we gained any direct evidence for life, but because the nearest possible address for such a discovery moved from somewhere distant and abstract to somewhere that has a name most people recognize, and a distance that, while enormous in human terms, is at least expressible without resorting to incomprehensibly large numbers. At the same time, the closer we have looked at Proxima Centauri and its planets, the more complicated the picture has become. The flare activity, the radiation environment, the questions about tidal locking and atmospheric retention, the contested existence of Proxima c. None of these are the simple, encouraging discoveries that early headlines might have suggested. They represent genuine uncertainties about whether the nearest potentially habitable planet is actually habitable, and they illustrate the gap between finding a world in the right place and understanding whether that world is genuinely capable of supporting life. That gap is productive. It has driven improvements in detection technology, as illustrated by the discovery of Proxima d, using radial velocity measurements sensitive enough to detect a sub-Earth mass world. It has motivated theoretical work on how planetary atmospheres survive or fail under the radiation environments produced by active red dwarf stars. It has pushed atmospheric modeling into new territory, examining the circulation patterns and climate states of tidally locked planets in ways that were not a priority before such planets were known to be common. And it has refined our understanding of what we actually need to know before we can say with confidence that a world is potentially hospitable. The Proxima Centauri system, frustratingly incomplete in our knowledge of it, has also served as a kind of template for thinking about the billions of similar systems that exist throughout the galaxy. The majority of potentially habitable zone planets that current surveys have identified orbit red dwarf stars, simply because red dwarfs are so much more common than sun-like stars. If the challenges facing Proxima b turn out to apply broadly to planets around active red dwarfs, then the number of genuinely promising candidates in the galaxy contracts significantly from initial estimates. If solutions exist, whether in the form of sufficient atmospheric mass, strong intrinsic magnetic fields, or biological adaptation to high radiation environments, then the picture opens back up again. The nearest worlds, in this sense, are not just destinations. They are test cases. The answers we eventually develop about Proxima b and its companions will inform how we think about every other red dwarf planet we find. They will shape the criteria by which future surveys prioritize their targets, and they will contribute to the long, careful process of moving from the knowledge that planets are common to the knowledge of what kind of planets can give rise to life. Chapter 17. The Universe of Possibilities. We began tonight just beyond the edge of our solar system, at the boundary where our sun's influence fades and interstellar space begins. We followed that thread of curiosity across 4 light years to the nearest star, and then to the planets that orbit it. Along the way, we have considered how those planets were found, what they are likely like, what threatens their habitability, and what their existence tells us about the broader distribution of worlds in the galaxy. It is worth ending with some perspective on where all of this leaves us, and what the scale of the question really is. The Milky Way contains somewhere in the range of 200 to 400 billion stars. Current understanding suggests that most of those stars have planets, and that many of those planetary systems contain multiple worlds. The total number of planets in our galaxy alone may exceed 1 trillion. Among those, the fraction that sit within the habitable zones of their stars by the simple metric of orbital distance is estimated to be in the billions. The universe is not a sparse and empty place. It is densely populated with the raw material of worlds. And yet, of all those billions of planets, we have characterized only a tiny fraction in any detail. Of those we have characterized, we have measured atmospheric compositions for an even smaller number. Of those, we have found nothing that we can currently interpret as a clear signature of life. This is not discouraging. It is simply an accurate description of where we are in an investigation that has barely begun. The tools needed to search for life beyond Earth in any serious sense, large space-based telescopes capable of spectrally analyzing the atmospheres of Earth-sized planets around nearby stars, are only now being designed and proposed. The era of actually searching, as opposed to preparing to search, lies ahead of us. What we carry forward from everything learned so far is a set of recalibrated expectations. The early excitement about exoplanet abundance, the sense that the galaxy must be full of Earth-like worlds simply because it is full of planets, has given way to a more nuanced understanding. Planets are common. Roughly Earth-sized planets in roughly habitable zones are not rare. But planets that meet the full suite of conditions associated with long-term habitability, stable atmosphere, protective magnetic field, temperate climate, steady stellar host, are a subset of that population whose size we do not yet know. and planets that have actually given rise to life are a subset of that subset, whose size we know even less about. The nearest planets beyond our solar system sit at the center of this uncertainty. Proxima b may be a barren, irradiated rock with no atmosphere and no liquid water. Or it may have found some way to preserve conditions complex enough to have supported chemistry of interest over geological time. We do not know. We may not know for decades. But it is worth remembering that the same uncertainty attended the question of whether other planets existed at all not long ago. And that question was answered. The universe is very old and very large and very patient. It has been generating planets and stars and galaxies for nearly 14 billion years, and it will continue doing so for far longer than that. Somewhere in all of that time and space, the same chemistry that produced life on Earth may well have operated again, and perhaps many times. Or perhaps the chain of events required is more demanding than any simple count of planets can capture, and living worlds are scattered only thinly across the vast dark between the stars. Both remain possible. Both are worth holding gently as we close tonight, not as anxious questions, but as open ones. The kind that do not need to be resolved tonight to be worth contemplating. The nearest planets are there, whether we sleep or wake, orbiting their dim red star, 4 light years away and patient as the dark.